So the electro discharge grinding, continuation from last slide, the conductive wheel usually is made of graphite and it rotates at 30 to 180 meter per minute in a dielectric bath of filtered hydrocarbon oil. So basically, the material for the cutting tools is which is a wheel, which must be conductive, is made of graphite. And graphite is kind of like a soft material that can be easily made. And usually, in average, it rotates at in the range of 30 to 180 meter per minute. And this is done in the dielectric bath of a filtered hydrocarbon oil, and usually this is kerosene. So the dielectric materials in the EDG, electro discharge grinding, is similar to the EDM process, which is kerosene. Right? And the workpiece is usually connected to the positive terminal of the DC power supply. So the wheel is connected to the negative power terminal, and the workpiece is connected to the positive terminal. So you have a voltage differential between the two. And the workpiece is machined using a stream of electric sparks. Each spark discharge melt and vaporize a small amount of metal from the workpiece surface. So the mechanism of material removal is similar to that of EDG, similar to that of EDM. So you're talking about the vaporizations of the minute amount of metals when the spark occurred. So this is a heat related mechanism of material removal. And the ratio of a volume of stock removed from the workpiece to that of removed from the wheel varies considerably, ranges from 100 to 1 to 0.12 to 1. So when you talk about how much material being removed as a ratio of material removed from the workpiece to that of to the wheel, which is tools, ranges from 100 to 1 to 0.1 to 1. However, the average is about 3.3 to 3 to 1. So every let's say, for example, every 3 meter cubic of workpiece removed, then you remove 1 meter cubic of the wheel. So it all depends upon the current density, workpiece material, wheel material, dielectric, and sharpness of the corner details. So these are the parameters that will influence the material removal rate, both on the wheel and also on the workpiece. So in terms of EDG process component, so basically you have the EDE phase, which is electrode discharge erosion phase. So in EDM process, then basically you have electrode discharge erosion phase. So the erosion happened due to the electrode discharge. And in this particular case, then you have a plasma, and the plasma is being developed between the metallic wheel and the workpiece. So you have metallic wheel is negatively charged, and workpiece is positively charged, and in between you have a dielectric. So when you have such a situation, then basically you can have if the voltage differentials and also the gap between the workpiece and also the tools is adequate, then basically you're going to have a spark. Right? You're going to have a spark, and that spark actually causes erosions and melting of or vaporization of the workpiece material. And basically based on certain study, this is studied by E. Hoffley in 1995. So this is an old study, but still remain quite valid. So if you look at the relationship between the removal rate and surface roughness, then is quite proportional. So there's some curvature on the curve, but it's quite proportional. So the removal rate, as the removal rate increase, then so will the surface roughness. So if you want to talk about, if you want to have a good surface roughness, then you have to have a low removal rate, material removal rate. And the reason being is, if you think about it, then if you have a high removal rate, high being that you have a high spark, high current, so on and so forth, then basically every time you melt the material, you melt in a bigger portion compared to if you have a lower material rate. So because of that, then you have a bigger crater due to the erosions of the workpiece material. So because of that, then you have a rougher surface. In terms of application, where these EDG usually be used, one is if you want to cut a steel and carbide at the same time without wheel loading. So if you use a grinding process, not EDG, then basically what during the grinding process of steel and carbide, then basically you're going to have pieces of steel and carbide, chips from the steel and carbide got embedded inside the grinding wheel. So once it's got embedded inside the grinding wheel, then basically you're going to have wheel loading. So if you have so this is grinding wheel. On the surface of the grinding wheel, then basically you're going to have a grid. You have a grid, and this grid of different shapes, and basically it's made of a very hard material. Right? So during grinding process, what happened is the workpiece from the so this is workpiece. So the material from the workpiece, either steel or carbide, will get embedded in between here, right? So when this thing is loaded with steel or carbide, then basically the cutting edge is gone, right? So basically when that happened, then you see that the wheel is loaded. So once the wheel is loaded with the workpiece material, chips from the workpiece material, then basically there's no cutting edge on the wheel surface. So because of that, then basically you're not going to have a proper grinding. You cannot remove the material using that wheel, right? But if you use EDG, then basically there's no contact between the grinding wheel and the surface of the workpiece. So basically, debris will be in the dielectric fluid, basically in the kerosene, and the kerosene will flush away. So you're not going to have a problem on wheel loading using EDG process. Second application is basically if thin sections of which abrasive wheel pressure might cause distortion. So if the workpiece that you're going to grind is consists of a thin section. So if you have a thin section in a normal grinding process, then you have mechanical force in between the two interface, between the wheel and also the workpiece. So basically, this mechanical interface will apply load, force, and also pressure on the thin section, and you can deform this thin section. So if you have such a case, then if you don't want to distort the thin sections of the workpiece, then this is your options, using EDG. The third application is brittle materials or fragile parts on which abrasive material might cause fracturing. So if you want to machine the workpiece brittle material or very fragile part, then basically if you have a mechanical contact in between the wheel and also the parts, then it can have fracturing on the brittle material. So to avoid then EDG is one of your options. Form tools and tungsten carbide throwaway bits for which diamond wheel cost would be excessive. So if you want to form a tools, on tungsten to form tools and tungsten carbide. If you want to use throwaway bead, which is a diamond wheel, so if you want to machine form tools or tungsten carbide throwaway beads, so this is basically cutting beads, cutting tools made from carbide. And basically you're going to have use diamond wheel. So basically this grid will be made of diamond, and the wheel cost can be quite excessive. So this is another reason why sometimes manufacturer or people turn away from regular grinding to EDG, because you don't have issue with having to have diamond wheel, which is can be quite expensive for the grinding process. Okay, so basically that's I think all about the EDG process. Next process that we want to talk about is EDM, but not regular EDM, but EDM using ultrasonic assistance. EDM with ultrasonic assistance. So when we talk about some other advanced manufacturing process last time, we talk about EDM, we talk about ultrasonic machining. So in this particular case, we combine the EDM with ultrasonic. But you don't have a slurry, you don't have a grid in the slurry. So the dielectric material will not have slurry. So mechanism of material removal in this case is not mechanical, but still heat induced. So the ultrasonic assisted EDM is a combination of EDM with ultrasonic vibration. So the ultrasonic portion of it is just the vibration portion of it. And the purpose of these vibrations is to improve machining efficiency. The way it improves the machining efficiency is basically by improving the dielectric flow in between the tools and the workpiece. The ultrasonic vibrations of tools or workpiece of dielectric fluid together with a low-cost DC power supply generates the discharge across the machining gap. So basically, you're going to have the ultrasonic vibrations either on tools, workpiece, or dielectric fluid. So there are three methods of applying the ultrasonic during this ultrasonic EDM with ultrasonic assistant. One is you can apply the vibration, the ultrasonic vibration on the tool itself, or on the workpiece, or on the dielectric fluid. In this process, the ultrasonic vibrations, usually frequency of about 20 kilohertz or above, is introduced during EDM process to improve the flushing efficiency of the process. So the efficiency of the improvement of efficiency, machining efficiency in the EDM with ultrasonic assistance is achieved by improving the flushing efficiency of the process. So if you can have a better flushing, then basically you're going to have a better material removal rate, because you remove the material out from the system and you keep the materials at the controlled temperature, and you can get a better efficiency of machining. Okay? So as mentioned just now, there are three ways of applying the ultrasonic vibrations, either on the tools, workpiece, or the electric fluid itself. Right? And all these three methods is still called ultrasonic assisted EDM. Okay? So if you apply the ultrasonic vibrations on the tool of the electrode, then the ultrasonic vibration is applied to the tool through the high frequency of a piezoelectric transducer that's connected to the tool. So basically, this is your tools, this is your tool electrodes. So behind it, basically, you have this piezoelectric transducer. And as mentioned, the piezoelectric transducer this material has a characteristic by which when it sees when it receives electrical signal, then basically it's going to expand And when the electric signal lost, then basically it's going to go back to its original shape. So the ultrasonic vibration is applied to the PZT actuator from the pulse generator. So again, we have a pulse. So the pulse will have a supply of power current to the PZT on and off, so that you have oscillating movement of the PZT material, which will translate into vibrations on the two electrode. The feed directions of the two electrode can be parallel or perpendicular to the directions of the vibration of PTZ. So the feed directions of the tool, so you can feed this material down, right? And the vibration, the feed directions of the tools of the electrode can be parallel or perpendicular to the directions of vibration of PZT. So in this particular case, in this particular case, let's say for example, this PZT is vibrating in this direction. You can feed the tools in this direction, also the same direction. Or PZT vibrate in this direction. You have tools over here, and you can feed the tools in the perpendicular direction, so the direction of the vibration of PZT. So both can. Both can. In this method, the tool electrode vibration, owing to the suctions of ultrasonic vibration, the dielectric circulations and debris removal are improved significantly. So during the process, as you have this pumping action of the tools up and down, that particular pumping action actually causing suctions, owing to suctions of ultrasonic vibration. The electric circulation is better. So as you pump it down, basically you have a suction and also high pressure, low pressure area. So you have a suction movement in between that particular tools and workpiece. So this improves the dielectric circulations, and debris removal will be improved significantly. So this is when you apply the ultrasonic vibrations on the tool itself. Right? You can also apply the ultrasonic vibration on the workpiece itself. The ultrasonic vibrations is a sum of sinusoidal wave with desired frequency are generated by the pulse generator and transmitted to the piezoelectric transducer. So you're going to have a sinusoidal wave. So the wave will be in the way the ultrasonic vibration in the waveform. So what it meant is sinusoidal wave, then basically you got to have wave as such. So this is similar to the wave generated during the ultrasonic machining process that we discussed during that topic, right? So with the desired frequency are generated by the pulse generator and transmitted to the piezoelectric transducer. So this is a similar mechanism as what we discussed when we talk about the ultrasonic machining last time. So, and for this case, the actuator is connected to the workpiece. So rather than just now, we talk about this particular actuator, PZT actuator connected to the tools. This one is connected to the workpiece through the plate. So basically, this is a workplace. So this is a joint plate, and this is PZT actuator. So it'll move up and down depending on the movement of the PZT material. During the workpiece vibration, the forward and backward movement of the workpiece causes changes in the spark gap and the electric field pressure with time, thus maintaining the sinusoidal relation of the spark gap and pressure difference with time. So basically, during this particular case, then this will move up and down. So it changes spark gap and basically also change the electric liquid pressure with time. So we'll go high, low pressure, high, low pressure. So because of that, then you improve the flow of dielectric fluid between the workpiece and the tools. Okay. You can also apply the ultrasonic vibration in the dielectric fluid itself. In the dielectric fluid itself. So the ultrasonic vibration can also be applied to dielectric fluid to create the turbulence into the spark gap between the electrode and workpiece, and effectively flush away the debris from the machine zone. So this is basically you have a tool holder. This is workpiece holder. So this is your workpiece. This is your tool electrode. So as this move down, right? Basically, you're going to have the ultrasonic bath. So usually in this particular case, there is you are attaching the ultrasonic vibration mechanism to the bath, right? To the bath. And basically that vibration will cause the dielectric fluid to vibrate itself, right? So because if it's vibrating, then it creates turbulence between the gap in the gap between the tools and the workpiece. So similar practice is being used. So sometimes if you go to the lab, there's ultrasonic cleaning bath. So the principle is the same. So in the ultrasonic cleaning bath, then basically vibrations that subjected upon the bath container will actually translate that vibration into a fluid inside it. So that fluid will cause the turbulence and will clean the debris from the items that you put in that particular bath. So similar to that, then you get to have a turbulence between the workpiece and the tools. So because of that, then basically you're going to improve the flow of dielectric between the gap. Right? So the material removal mechanism for the EDM ultrasonic assisted EDM process basically employs the electro discharge phase for melting and evaporations of the workpiece material by the plasma channel in similar way to normal EDM process. So material removal mechanism similar to EDM process. So the ultrasonic vibration itself, the purpose of it is basically to improve the flow of the electric fluid. So if you remember, when we discussed about the ultrasonic machining process, the ultrasonic machining process, the mechanism is basically mechanical means of creating a crack fracture on the workpiece, and then and that particular crack fracture is being removed by the fluid. But for this particular case, there is no grid, hard grid inside the fluid. So basically, the removal mechanism is due to heat, electro discharge phase. The intensity of the discharging action depends on the working conditions such as gap, voltage, amplitude, frequency of the ultrasonic vibrations, as well as the gap flushing condition. So the intensity of the discharging action depends on the working conditions such as gap voltage, amplitude, so on and so forth. And include in here, which is missing in EDM, regular EDM process, is the frequency of the ultrasonic vibration. The reason of this is basically, the gap between the tools and the workpiece will keep on changing because of this ultrasonic frequency of the ultrasonic vibration. Because of that vibration, so the gap will keep on changing. Because the ultrasonic vibration of the tool, its front surface moved down towards the workpiece surface and the electrical field intensity increased. So during the downward motion of the tools during the cycle, ultrasonic cycle, then basically the front surface moved towards the workpiece surface and electric field intensity increased. So because of that, because the narrower gap, then basically the electric field intensity going to increase. The electric field, however, caused the ultrafine particle metal debris ejected from the formed crater. So because of that, the electric field, how cause the ultrafine particles of metal debris, which is rejected from the form craters in the machining medium to the suspended and form a bridge across the gap. Cause the ultrafine particles in the machining medium. So machining medium is the dielectric field to be suspended and form a bridge. So basically, you're going to have this debris, this debris in between the gap, suspended in between the gap, and sometimes it's form a bridge across the gap. Right? At a very small gap size, the ionizations or breakdown of the working fluid occurs, and plasma channel is formed. So at that particular when the gap is small, when the gap is small, then basically a similar mechanism to that of EDM process. The ionization or breakdown of the working fluid occurs. So because of that, you're going to have a plasma channel form. And when the tool front moves up, but when the tool front moves up due to that vibrations, so if, as it moving down, the gap closer, then the gap become smaller. Then you have a breakdown of the ionization or breakdown of the working fluid. Then you have a plasma channel form. Right? But when the tools move up, the gap voltage arise. So the gap of the voltage arise, and because of that, basically voltage arise, then the current will drop, and the plasma channel collapse at a large gap size. So this process begin when the tool moves down again. So due to that particular vibration, this is repeated. This mechanism is repeated, but still the means of material removal is due to the heat, due to the electro discharge phase. Right? And it will melt the materials, the workpiece material. So when we look at the compare between the material removal rate between the ultrasonic aided EDM and also traditional EDM, we can see quite a significant difference between the two. So when you talk about copper, then you can see that you're talking about 300 times better if you use ultrasonic aid EDM compared to traditional EDM process. Similar data can be seen when you machine stainless steel. So this indicates that the material removal rate for ultrasonic aided EDM is much better compared to EDM process. And when you look at the MRR and the surface roughness comparison between EDM, USM, ultrasonic EDM is EDM, ultrasonic discharge machining process, USM, ultrasonic machining process, and MUS is the ultrasonic assisted EDM process. So EDMUS stands for electrical discharge machine with ultrasonic assistant process. Right? So if you compare these three processes, right? Depending on materials that you machine, which is SG4 ceramic or SiC, and we're looking at the material removal and surface roughness. So in terms of material removal, you can see quite consistently that EDM ultrasonic EDM process is much better compared to EDM or USM process. And comparing EDM and USM process, EDM has a better material removal rate compared to USM. However, when you talk about the surface roughness, surface finish, then USM is performing much better. So if your concern is with if surface roughness is critical for your process, then basically USM will give you a better surface finish. Worse is EDM, and comes ED, MES. Ultrasonic assisted EDM process. In summary, for in general, the material removal rate is much better in EDM, ultrasonic assisted EDM process. However, in terms of surface roughness, then USM is much better compared to the three processes. So ultrasonic EDM process material removal rate is about 3 times greater than that of USM, and 2 times greater than conventional EDM process. Moreover, the surface roughness of the hybrid process is greatly reduced to 1/3 of the normal EDM process. So there's improvement in terms of surface roughness between EDM and ultrasonic assisted EDM process. The surface roughness produced by normal USM is 40% of those machined by electrical discharge machining with ultrasonic assisted. So, however, USM ultrasonic machining will give a much better surface finish compared to even ED MES. This is because in the ultrasonic machining process, the mechanism of material removal is due to the grid that's inside the slurry, and the grid is very small particle grid. So the material removal rate by the grid is going to be very slow and very minute. So because of that, then you can actually get a very good surface finish using USM process compared to EDM and ultrasonic assisted EDM process. So basically, those are the hybrid advanced machining process that will be covered in this particular topic. So hopefully, you can actually appreciate the differences between the advanced manufacturing process itself and also the hybrid advanced manufacturing process in terms of the basic principle of material removal and how it improves the material removal rate and also the surface roughness. So that's the end of the lecture for this particular topic. Thank you.